It's a pleasure to talk to so many specialists in this field and also discuss because I'm working in research. It's always nice to see actually build buildings in earthen materials. We saw a lot today, and now we go more into research and a bit more into details. And I hope it's not too detailed at some point. I try to integrate a lot of videos and pictures to show you, because usually I'm used to speak to research audience, and then of course the topic is a bit different. So I try to give a broad picture today of robotic aided fabrication of rammed earth elements. So I'm working as a research assistant at ITE in TU Braunschweig under Professor Harald Kloft and Professor Norman Hack. And I studied architecture and building technology in Braunschweig and Delft. And at some point I fell in love with robots and earth somehow. And then after my studies, there was the question, what do you do with these passions? So I came to the Institute of Harald Kloft and Norman Hack, who are dealing with additive manufacturing and construction and research projects in that field. So at first I would like to show you a bit what we do at the Institute. This is our team. We are a team of architects, engineers, and designers and technicians as well. And we are doing, on the one hand, we are doing research projects, which I will show you. And on the other hand, we have teaching activities as well for architecture students, always related to additive manufacturing and construction. This is one big collaborative research center, interdisciplinary. It's called AMC, Additive Manufacturing and Construction, and it's a collaboration between TU Braunschweig and TU Munich. It started in the beginning of 2020 with the aim to fundamentally investigate in the possibilities and challenges of additive manufacturing and construction on a really broad scale. So the aim is to investigate in a broad variety of material process combinations, and therefore the basic structuring, which you can see here, of the currently known methods for particle bed and deposition techniques, here on the left and on the right, were assigned to the traditional materials concrete, steel, wood, and FRP. So in this case, there's no earth involved because it started earlier, and the earthen projects are not in this AMC right now, but will be probably in the future. So to the general structure of the TRR-277, it is divided into three main areas, focusing on innovative and resource-efficient material process combinations in the A areas, computational modeling and process control in the B area, and design and construction in the C area, where the additive manufacturing processes are linked to the planning environment and the construction site. So altogether, the AMC has 18 interdisciplinary projects with 29 project leaders in different fields. This is our research facility at the TU Braunschweig. It's called the Digital Building Fabrication Laboratory. That space is kind of the center of all our research activities. So few words on that. There are two gantries, and we have one industrial robot, a 6-axis, and we have a milling machine on the other side with 5 axes. And the idea is that both machines are able to work cooperatively on building processes with different materials. Here you see the shotcrete 3D printing method, which was developed in TU Braunschweig, where different to extrusion-based processes, the material is actually sprayed and accelerated in the nozzle by air pressure, and therefore it is kind of shot on the subsequent layer, which makes the bond between one layer and the next layer way better compared to other 3D printing techniques like extrusion. On the right side, you see a section of a created element You also see that the layers kind of compact in a very nice way. Yeah, in general, it is about reducing material, reducing mass, and with these additive manufacturing techniques and with this shotcrete 3D printing method, we are able to create different types of elements, such as here columns, wall elements, spatial beam structures, or also horizontal elements. We talked about the Nervi roofs before. And there's another junior research group at TU Braunschweig called Future Open Coastlines that deals with coastal protection and looks at the benefits of additive manufacturing and coastal protection. It's a collaboration with the Leichtweiss Institute for Hydraulic Engineering and Water Resources, long name, at TU Braunschweig. So that's what we do in general at the Institute for Tragwerksentwurf, but now I will go into earth and materials. As a little introduction, we heard a lot about what is earth and what is clay. I just want to say one more thing about that. Here you see the hydration process of concrete, where on the left side you have the mixing water and the aggregates and chemical binders in the mixing state, and on the right side you have the same material but after hydration. And what happens on the outer blue ring that you see is the leftover water that need to leave the structure. So a lot of the water that we actually mix in is bound into the matrix. That's why we don't have such a big problem with shrinking in concrete compared to earth materials. So now we have the same graphic but in earth materials, and what you see is that drying through evaporation, this part is way bigger because all the water you put into the material actually needs to leave the material again. That's why for us it's really important in additive manufacturing, because there are some techniques that focus on pasteless material that you need to pump. If you need to pump a material, it needs to be fluid, so you need water, but this water needs to dry out again in the end. And that's why if you have a pumpable material, you have a lot of problems usually with shrinkage and with change in the geometry afterwards when it's dry. We have seen kind of the same picture before. I don't want to talk about it too much. It's just the 12 most important traditional building techniques in earth. Here, the middle part, this middle ring, you see that it focuses actually on the humidity of the material, or the viscosity actually. So on the state of the material that you need it for when you want to process it. Here it's zoomed in, recreated but zoomed in. You see there's the dry or solid section, there's the humid section, there's the plastic section and the liquid section. And as I said before, extrusion-based manufacturing processes, they need this, where we have this blue ring now, liquid or plastic state, so you need more water compared to the humid state, where the rammed earth is located. So in additive manufacturing, for us it's really interesting to look at the material that has the least amount of water possible, but afterwards we are still able to bring it into form. And that is what rammed earth actually gives us, because it has way less problems with shrinkage. We don't need to pump the material, and so on. It doesn't make the whole process easier, because if you cannot pump the material, you have to deliver it somehow. So you need to come up with new ideas. So that's the reason why we focus on rammed earth and not, there are a lot of other additive manufacturing techniques with earth, like 3D printing or sprayed earth as well. Yeah, now I come to the project itself, and here on the photo you see everything that is needed for traditional rammed earth construction. There's a tamper, there's a formwork with tensile connectors in between, and there's a suitable earthen material and a lot of manpower, of course. We have seen the pictures in the middle and on the right from you before. You again see on the right side, the picture is from this year. It's like 3 months old. You see again the most important things. You need the components for rammed earth construction nowadays if you want to build in situ. So again, it's a temper, a formwork with tensile connectors in between, suitable earthen material, and a lot of manpower. So of course the tools itself changed quite a bit during the time. The temper is, for example, a pneumatically driven one nowadays, and the wooden formwork is able to withstand tamping forces equal to 60 kilonewtons per square meters. But the general process logic stayed the same. A formwork is placed, raw materials delivered, and subsequently fed into the formwork. You see it in the middle picture, where it is compacted in subsequent layers. Here, more than 50% of the expenses are actually formwork related and not due to material compaction. So now the main idea of the research project was that, I go back to this picture, on the right side you see me tamping in the formwork. You have this whole formwork built up, but you actually only need the formwork in the moment where you tamp at a specific location in the formwork. Right afterwards, the material is strong enough that you could remove the formwork immediately. So the idea, after realizing that, the idea of transferring or using additive manufacturing for increasing this process was that you activate the formwork, so you just have it exactly where you pneumatically, or however you want to do it, you are compacting the material. That means here, in this case, it was a student project from one of our seminars. The idea was that the formwork, the slip form, is connected to a robot. Here is a UR5 with a pneumatic tamper in the middle, and there's a material delivery here as well, and it just goes where the material should be compacted. So we can reduce the formwork quite a bit compared to the traditional in situ technique, and actually just use it where we really have to use it and not waste the material for the rest. This is a little video of the student project. It was kind of our small-scale proof of concept that it actually works with a sliding formwork that is activated by a robot and this tamper. Seeing these small-scale attempts as a proof of concept, as I said, the next challenge was to scale up the setup for one-to-one building scale. And how do we do that? Of course, if we look at the traditional construction technique, we have to reduce the weight, the general weight that we have to lift, because robots can be strong, but they're not infinitely strong. So this is some point we really have to look at, the weight of the whole system in the end. To reduce the weight, we can say, okay, now we have we saw that we can reduce the formwork size, which reduces the weight, of course. Then we should also reduce the formwork stiffness, because less stiffness means less weight. If we want to reduce the stiffness, we have to reduce the compaction energy, because the compaction energy and the stiffness needs to be related, of course. So the goal, or the key factor actually here, was to reduce the layer height. If we reduce the layer height, we need less compactive energy to make one layer as strong as we would make a layer that is 10 centimeters high or something. So the higher the layer, the higher the compactive force you need. So instead of up to 10 centimeters that we use in, let's say, the traditional construction, now we wanted to investigate in layer heights around 2 centimeters. Here you see the first draft of an end effector mounted to a robot arm with an actively controlled slip form and compaction device. So it's still kind of the same concept that we saw in the student project, but now bigger, and the compaction itself, it changed to a vibration plate because we are able to control the vibration plate to the speed of motion and these things. So in the end, the robot only holds the slip form, and the vibration plate gives the speed of motion. So it's laying on the earthen element. Here you see that the vibration plate here, it's number 1. It is not connected to the robot, so it's just laying on the earth, and the robot is just holding the slip form where the vibration plate is at a specific time. So again, the whole process started with this very first proof of concept, where it was like a manually formwork that where we just placed the tamper manually in between and looked at if it's actually feasible to do that, because you also have friction between the formwork and the earth. Of course, if you compact the earth in such a formwork, is it actually still movable? These things. Then we scaled it up to first robotic experiments on the UR5. Then there was the first prototype build that is based on the drawings that we saw before. I will show you some more pictures on that, and then prototype 2 I will show you later. So here, this was the first one-to-one prototype. It was also based on a student project that we had at TU Braunschweig with architecture students. And here you see on the right side the element that we created in this course. And on the left side you see the end effector with the shuttering, the slip form, hanging on the robot in between the compaction device. And then we had on the front and on the end we had small pneumatic tampers for the surface compaction. Here we also figured out some challenges that we will face scaling or working with this further. One is here an insufficient stiffness of the slip form, so even the small layers, they need some compactive force, of course, and here we underestimated that a bit. So we needed to change the system. The geometry of the vibration plate needed to be optimized. The pneumatic tampers were not sufficient. We saw that on the outer surface, and here the material feeding was just done by hand, so we didn't think about that because you go from step to step, of course. And the slip form should be operable in case you want to take the whole system off and on again. So then I hope it's playing. Then we animated the process as we wanted to go further. So there is a cooperation between the CNC, two portals that are showed in the beginning. One is delivering the material, the other is doing the compaction. Here you see all the elements that are in there. There's the slip form again, there's the compaction device, and like this, subsequently 2 centimeters by 2 centimeters, the wall element is built. That was the idea. So that was how we actually did it then. Yeah, you see the same devices. Of course, some things changed. Here the material feeding device on the second portal looks a bit different now, because we had to reduce some costs in the project. I will also show you a video, but the most important thing is that we are working with in a cooperative process. So it's not actually one process that is feeding the material, compacting it, and do the shuttering, but it's material feeding plus the shuttering and compaction. Here you see a video on the feeding device. So it is fed manually into this machine. Then the machine comes and delivers it to the specific location. So here it's around 3 centimeters of layer height uncompacted. So it brings it where it needs to go. Then it closes and goes off, and then it goes off and goes to the position where it's fed again. So for this size of of machine, we can feed 2 layers of material, and then it needs to be refilled. Also, the compaction device changed quite a lot. We integrated stronger pneumatic tempers on the face sides of it. There's a steel plate and an unbalanced motor again, which is together the vibrating plate for compaction. And here the number 2 marked is also the connection between the temper and the vibrating plate. Now to the slip form and compaction process. So number 1 is the robot that is able to precisely position our slip form. Then we have a steel frame, this actively guided slip form, these panels, and the compaction device in between. And now I think, I have a video also on the compaction process. So the material that was fed before is compacted. I think the pictures talk enough. So there was the second, the second development of this end effector. Then of course it's a research project. So in order to evaluate the compaction process, we performed some studies with different compaction parameters, because there's quite a broad range, of course, also when we talk about different layer height. So here, I think you're not able to read everything. It's also not necessary. We just performed some tests. You always do minimally 3 cubic test specimen that you test on compressive strength. On the right side, you see compressive strength of different specimen that we did. And in the first test, which is the blue one here, that is now marked in red, you see the blue lines on the right side. You see that we used, I need to look it up, we used a layer height of 5 centimeters, uncompacted, a material with a maximum grain size of 8 millimeters, a vibrating plate with a frequency of 30 hertz, and this resulted in, like from single values, the highest compressive strength we could achieve, but the deviation, you see it here on the right side, was 25%, and that was way too high for us, because what we actually aim for is a very low deviation between different samples, because of course it's an automated process, and the goal is to have actually no deviation, because we can control the whole process, and it's not related to one worker that is temping there. So the next 3 specimens here, we see that the material was just too coarse. We used a material of 0 to 22 millimeters with a layer height of 3 centimeters, and that led to very low compressive strength and also very high deviation between it. So there's a boundary reached, let's say. And then the last 3 specimens where we used the same setup, we had 3 centimeters of layer height, up to 8 millimeters of grain size, and we achieved a reasonable compressive strength for our first tests and a deviation of only 3%. You see the red lines on the right, they're quite in a similar range, and that's what we actually aim for. So this is our benchmark value from where we want to go further. So on the left side you see a second element that was produced in DBFL, and on the right you see the surface structure, which is different to, I mean, here are pigments so that we still see the horizontal accentuation, but you don't really see the layers anymore. And here we see on the left side, I think a layer height of around 8 or 9 centimeters. And on the right side, you see our layer height. And on the left, you see that it's of course visible. On the right, it's not visible anymore. but why is it actually visible, and why do we want to see it? It is visible because we are able to compact on the top. We compact one layer very good. So here it's very high compaction, and up to the end here it gets less. So that's why we have this horizontal accentuation. So it's actually it's not fully compacted material that we see. So that's a big discussion in our group on where to go further, because people, if we talk to people that want to work with this technique, they also want to see that it's compacted in layers, of course. Yeah, that's an ongoing discussion right now, how we deal with this, but yeah, from our perspective, it makes just sense also here to aim for the better compaction. Another part of the research project funded by Zukunft Bau, I need to say, I think I didn't say it, in Germany, was the subtractive post-processing of rammed earth elements at the DBFL, and we were looking at how to best cut these elements. And I think I have, here. So the aim was to look into dry connections between elements. Right now, if we are producing elements and bring it to the site, we are connecting it with concrete sometimes. So the elements horizontally are connected with concrete. That's something that we can make better, let's say. So the aim is here to look at dry connections and to highly precisely define the connection type, or the connection. Yeah. On the right side, you see how it looks when it's milled. On the left side, you see it with a milling saw, with a saw blade, circular saw. And yeah, we made some tests with it, comparing elements that were still wet that we post-processed. So if you post-process a still wet element, shrinkage will happen afterwards. And if you post-process an already dried element, then shrinkage is already done. And we just wanted to see how the results in post-processing look on dry elements compared to still wet elements. Here you see a hint already, and here you see it in more detail. So if we post-process the elements in the wet state, the cut itself gets way more precise. You see it on the top, and on the bottom you see when we cut it in dry state, which would be beneficial for the shrinkage issue. Then we just have way more material that is yeah, kind of carved out, and so the precision just is worse. I'll leave you with that information. Now I want to, these are my 2-3 last slides. There will be a new research project coming soon at our institute. It is called Mobile Robotic Rammed Earth from the lab to on-site production. That's what we want to do. And there we want to look at at the utilization of locally sourced raw materials, because right now we are using material from the industry, because this is not our field of expertise. But here we are working together with Material Institute at TU Braunschweig, and so we can deal with this area as well, because I think it's quite an important area when we talk about clay, or building with clay. Then raw material optimization, mobile robotic production unit that we are building, so it's in the field of robotics and process development, that is actually able to go on site and produce, and of course there will be tooling. There will be parts where we look at tooling for material feeding, we saw it already, material compaction, and the slip form, which need to be developed further, and for the on-site environment. Yeah. So yeah, that's a picture for what we aim to do in the coming research project. And that's it. If you have any further questions, you can always contact me. You can also look at our YouTube channel or Instagram channel, and or just contact our head of institute, Harald Kloft and Norman Hack. Thank you.